Okay, so good morning, IPIN participants. The session we're about to do for the next 75 minutes is a re-presentation of 3 of the papers that were nominated as this year's best papers. Before we begin with the first of the 3 nominees, I would just like to say I would like to thank the TPC for the review work that they did for this conference, and also just point out to everyone else that there were the task of picking out 3 top papers was actually quite difficult. And so we looked at all of the review comments, and then we sent a large stack of highly reviewed papers back around to another smaller committee, and they returned rankings, and we were able to form a consensus on 3 papers that were very good to read and very interesting. And so we're now going to see those 3 papers again. So our first presenter, and I've been practicing his name and I'm going to get it wrong again, is Yu Jae-hyun. And he is, come on up, you're on. He is going to be giving a presentation about mapless indoor localization by trajectory learning from a crowd. And with that, I'm going to hand the podium over to you, and you've got 20 minutes. So.
Thank you. All right. Thank you for introducing me. And this is a great honor to be standing here to give my presentation. It's just about mapless indoor localization. And my name is Jae-hyun. Thank you. And sorry for wrong date. This is 7th. And I'm working for the KTH, the Royal Institute of Technology in Stockholm, Sweden. And this work is collaboration with the SNU in the South Korea. So this work considers a little special situation where we cannot use map information. So it is reasonable sometimes because it's sometimes impossible to obtain and hold map information. Because first it is related to privacy and security problem. So I have experience to ask the Seoul Central Station about the map information, but they answered no because they want to keep the security for the Seoul Central Station. So we have to consider sometimes where we are not given map information for the navigating system. So one of the solutions this work suggests the trajectory learning from a crowd. So here is the basic underlying idea about the crowd learning. So here is, I assume, the simple map. And if there are people on the map like this, and when we obtain the data from them, and if we can project the data onto the 2D space like that. So the map information is exactly similar to the trajectories of the crowd. So I'm insisting that we can use the crowd data for supporting absence of the map information. So here is why crowd learning is beneficial to the indoor or outdoor, the navigating system. So first reason is there are a huge amount of training data. Very good example nowadays, we can see the smartphone game, the Pokemon Go. So they have a lot of the clients over the world, and maybe we can project the data to the global map. So we can obtain the precise map information without help of the GPS. The second one is qualified training data, means the obtained data from the crowd are already results of the localization system. So which means it's better than the low sense observation. And third one is major point of the crowd learning, up-to-date training data means, so here is a simple example. There is one here departure from the staircase, and there is destination. The most of people maybe goes to straight to the destination. But here it happens the construction. So if this area is blocked by some reason like construction, floor cleaning, the people tend to naturally find the optimal path in the indoor environment, which means even though we are not given map information, the crowd data represents the up-to-date date, the change of the environment. So this is a very important characteristic when we use the crowd learning. So here we go, is the problem setup. So first one, of course, we are not given web information. And second, we are gonna use only Wi-Fi RSS data as the sensor observation. The reason I used only Wi-Fi RSS in this work, I don't want to make a restriction to the users. Such as the PDR or phone-mounted the navigation system, we have to restrict the posture of the users, but I don't want it in this work. But this does not mean we have to only Wi-Fi RSS. I'm gonna show you later on. We can use, of course, the other kinds of sensor in this work. And the final assumption, there is one service provider, which means the centralized system. This centralized system can collect crowdsourced data and can do the localization and can give back to the users the localization result. So this is the basic framework of the localization in this work. I used particle filter. I'm gonna show you very briefly about particle filter. It has two separate steps. The first step is sampling. It will spread particles, equal sized particle to the predicted location. And in the second step, it updates the weight, the volume size of the particles. So in the sampling step, we used to have the hold and prior function. And update step, we use the likelihood for updating weight of the particles. So I'm gonna show these two different prior and the likelihood. So first, I'm going to show the general prior, which are used for the general case situation where we can have map information. So first, the p distance function shows it gonna restrict the distance of the current step and the next step by using information of the human velocity. But I want to say the accurate velocity of the user using only smartphone sensor is not that accurate, I just assume. So I don't want to use any information of the users using the smartphone sensor. So it will be replaced by the other function. And here's the map information function is we can use it when you are given the map information. So I suggest the alternative prior function here. So instead of using the information of the velocity, estimating velocity of the smartphone user, we can replace it by this function where it does not have any information of the users. So, and then the peak crowd function will be defined by the crowd learning later on. Now, I want to say the likelihood. The likelihood function, as I mentioned, is used for updating the weight of the particles. So in this work, the Gaussian process is used to model the relationship between the sensor observation and the positions. So the reason why do we use Gaussian process for the model likelihood? The first, the Wi-Fi RSS observation is very nonlinear, noisy, and uncertain over the indoor area because indoor environment, there are a lot of obstacles, walls, which means the loss path is very unpredictable. So the machine learning technique is known as one of the solution for the unpredictable situation. And second reason is the likelihood function is based on probability. And Gaussian process is based on probability, which means without any modification, we can directly apply Gaussian process for defining likelihood function here. So the likelihood function is defined as the Gaussian distribution whose mean and variance is like that. So the Gaussian process, you can see a lot of papers nowadays. Of course, in this conference, it's very, very popular these days. In my personal opinion, Gaussian process, the major advantage is very simple coding. I mean, it's very, very simple to program it. To be honest, these two sentences are all of the Gaussian process. So this slide illustrates the result of Gaussian process in terms of that it can represent the Wi-Fi distribution over the area. So here is the test bed where 8 different Wi-Fi access points are there, and we gotta focus on number 3, and its distribution is here, and we can figure out the higher the strengths remain in the loom because the Wi-Fi access point in the loom, and as the distance from the AP is decreasing, the strengths will be decreased also, and we can see the non-linear and very noisy situation. So from now, I'm going to talk about trajectory learning, which is a major concept, major point of this work. I'm going to say first the concept of the trajectory learning. So I have the basic assumption here. The people tend to walk similar trajectory when we are having the same departure and destination. Imagine that there is the starting point and we want to go there. Most of people probably goes to there because there are only the short path here. So we have to convert this sentence to the equation. So I consider the statistical view. There exists an hidden intended trajectory Z that can be representative of the other samples X. So for example, the red line G can be average trajectory of the other all samples. So we need to make a more realistic scenario because the people have the different speed. We work at different speed, so the trajectory samples can have the different lengths. So which means we have to consider the time synchronization between the samples. And there may exist outlier here. I'm going to show again example. This is most probable trajectory, I assume. But we can see there is a super narrow collider here. Maybe a kid, or a very brave person is willing to go the narrow aisle to approach destination more quickly. He is willing to squeeze himself to the very narrow aisle. So in the big data, crowdsourced data, we have to consider always the outlier. So the algorithm need to consider we have to detect outlier and we have to remove outlier for improving whole average accuracy. Okay, here is the problem formulation for the trajectory learning. The goal I made is to find one hidden trajectory Z, and I make a model as like that. The hidden trajectory Z has the own dynamics F, and of course we don't know, the F is unknown, and it has the probabilistic noise, which has the covariance Z, and all the other samples come from that one hidden trajectory, and it also has the covariance. Because I assume that sample trajectories have the different lengths, the time synchronization, the index tau has to be considered in the equations. So here is the optimization problem. I want to maximize the log likelihood function, but the different covariance and the tau, this time synchronization index, it's difficult to optimize them at the same time. So I found one interesting paper which separate the steps, and they iterate 2 separate steps to converge the converts the optimal solution of this optimization. So it introduces two different steps called Kalman smoother and dynamic time warping. So Kalman smoother plays a role when at the fixed tau, it's gonna find the covariances, and in the step of the dynamic time warping, at fixed the covariance obtained from the Kalman smoother, it finds the time index tau. So I'm gonna explain with illustration. It's more easy. The Kalman smoother again is to find one regularized trajectory among the samples. So here is the simple test. I'm given 6 different trajectory samples, and Kalman smoother finds one regularized trajectory here. Actually, this trajectory is the exactly trajectory what the tester user moved along. And then in this step of the dynamic time warping, it's gonna match the different time synchronization between the hidden trajectories and the other samples. So like this, it finds the time sync to the all points of the learned trajectory Z. So I guess the battery is out. This does not work. I need help. There's something advertisement popped up.
No. Okay, keep talking.
You have to give me more time.
Okay, you've got 5 minutes.
So here is the result of the iterations. So 2 steps. So after iterations and convergence, the learned trajectory becomes more smoother and natural. Please find difference between this result at the first iteration, and this is the after maybe 10th and 20 iteration after result. So outlier detection. Here is the sample. We can examine the covariance of the samples. So technically and fundamentally, the covariance means the difference between the sample and the hidden trajectory. So here is the test. I insert one outlier to the 6 trajectory samples, and we can figure out it has the very outstanding norm of the covariance. So we threshold it and remove it. Okay, until now I showed the trajectory learning when we are given the sample trajectory. But the question remains, how do we sample the trajectory? Because the trajectory has this start point and end point. So we have to cluster these sampling trajectories. So this work suggests a landmark detection, which are defined as particular sites. So we are given only Wi-Fi sense observation. So here is again machine learning technique in order to find the pattern of the varying decibel of the RSS at the different landmarks. Idea is the combination of LDA and PCA. There are problems, the fundamentally dimensionality reduction problem, which use the eigenvalue problem, which means we can select major components in the low sense observation. So here is the 5 different landmarks, and the result of the feature extraction shows different landmark data points shows very recognizable understanding. So when I define the distance metric is on the signal space. So it's not the 2D space. So we can see when the user moves the different landmark, the distance metric shows the decreasing and increasing according to movement of the users. So again, I can threshold it, and we can detect whether or not the user is on interesting landmark. Okay, here's the experimental result, and I'm gonna make it very quick. So here's the result of the one floor, and the proposed method which I used to learn the trajectory has the similar result when using the true map information. And if we do not any information over the map, it has the difference of the 1 average meter. And I want to show the interesting video. It's interesting to me. I'm not sure you are interesting. So here is the video clip where landmark detection, how the landmark detection is processed during the movement of the user. So user is approaching different landmarks, and the landmark, please shows the yellow line. The yellow line distance metric is decreased when the user approaches that landmark, and it again increases when the user goes to the other side. And here is the launch trajectory from crowd. I employed that colleagues without money, and this is a result of 3 participants. So what's the point in this video clip? As the more participants join in the learn trajectory algorithm, it gets more accurate. It gives us more the smoother, accurate learned trajectory. So this is 6 crowd. And when I make it 10, the result becomes more fluent. So let me recap the result of the learned trajectory on 2 different floors. You can see that 13th floor has only aisle and corridor, so it's more easier than the 14th floor because it has the more open space. And this is the result of the particle filter, how the particle filter is processed. So I'm gonna make concluding remark. I assume there's no information and situation, and I use the particle filter, and prior and likelihood functions are defined by web learning and Gaussian process. So I improve localization result by our learned map, and I'm gonna extend this result to the more big size of experiment, because in this work I just employed 10 people, but we need more and more crowd, because it is hard to say the 10 people is the crowd. Okay, this is the end of my presentation, and thank you for listening presentation.
We may have time for one question, and I think there's a microphone on the floor. Is perfectly clear? Okay. All right. Well, thank you. Thank you once again.
No.
Oh, you found a question.
Yeah.
There's a question. Oh, okay. You don't get to leave quite yet then.
Yeah, don't make me marginalized.
We only have time for one though.
Hi, thank you for your presentation. I liked it very much. But I wondered, you state that there's no map information, but from your presentation, I gather that you do know where the Wi-Fi access points are. Is that correct?
Yes, it's very, very good question, and maybe you misunderstood. I think we don't need to know the positions of the Wi-Fi because we're gonna use the Gaussian process, and training data includes the Wi-Fi observation and the position of the users. So we don't use the positions of the Wi-Fi access points. But you know, the situation, I'm gonna explain the example. So I showed where is the Wi-Fi and showed the result. But please remind again, we don't need to know the positions of the APs. Thank you for your question.
Okay. Unless there's a really quick question, we're going to move on to the next presenter. Thank you once again, Jae-hyun. All right, our second of the 3 nominations is a paper that will be presented by Alexandre Verviche-Piquoise. And in the interest of time, I'm just going to let you get talking. All right? Okay. Good.
So thank you. Good morning. Well, I'm going to present you a GNSS-based technique, okay, in order to carry out positioning, indoor positioning. But here, our goal will be to evaluate the potential accuracy of the system. Well, this is a table, okay, tables that are presenting some techniques, okay, indoor techniques. So of course it's not an exhaustive table with very, very potentially polemic criterions. Okay, so our goal here is to to show that there are lots of solutions, but amongst all these solutions, one is very particular, one is historically particular. It is GNSS solution, GNSS-like solution. Why? Because it's not a new information for you. GNSS are everywhere. And more particularly, GNSS device, GNSS receiver are everywhere. Okay, here you can see in smartphone, you can see in any kind of users, and this is very particular. So if you type in your Google Play Store GNSS, you will find potentially a lot of application. So it means that GNSS, and more particularly GNSS receiver, is very specific. Well, of course, it is a long story. Since at the beginning of the outdoor navigation, of course, I think we all agree that GNSS has totally transformed the perception of the positioning, and introduces and has introduced the positioning in our life. So, at the first time, the idea was to ensure the continuity of the service, including very difficult environment. So it is what we have summarized here, the development of GNSS, because, of course, when you are indoor or when you are in a difficult environment, signals are generally too weak, or are very affected by multipass or any other kind of problem. And the idea was to use signal processing technique to improve the capacity of the receiver to carry out positioning. So there were high-sensitive GNSS, improves the sensitivity of the receiver, assisted GNSS. Another idea was to include new constellation, because with more satellite, there are more possibilities to improve positioning. So it was the idea. And something that we are going to focus on, the use of local generator, okay, which is called pseudolite for pseudo-satellite. And the idea is quite simple. It is, for example, in this room, okay, we cannot receive GNSS signal from the satellite. Okay? So the idea here is to add new transmitters, local transmitters, okay, in every corner of the room, for example, and these transmitters broadcast signal, okay, GNSS-like signal. So for a receiver that works outdoor, it will be the same signal and the same kind of processing. Okay, so it is the idea of the local generator. And of course, idea of hybridization to improve positioning. Okay, so this slide presents some pseudolite-like method. Okay, and you see here. Oh, sorry. And you can see here that there are different interesting methods that and problematic that are that are encountered when using of pseudolite. For example, the problem of pseudolite is that you have near-far effect. You have the problematic of the synchronization, because outdoor the synchronization is ensured by US Army. Here, if you use a local network, you need to synchronize yourself. And of course, multipass in every outdoor environment are very, very, has very, very important effect. Okay? So, different variation of pseudolite in order to mitigate some problem, repeater, to mitigate near-far, etc. But the main idea was, and repelite, in order to simplify the synchronization. So I'm not detailing all this method, but the idea is finally to use what is the main, the question is what is the main problem with indoor positioning? It is multipass. And GNSS has a possibility of measurement, which is carrier fair measurement, which allows, which are less sensitive to multipass. So it is interesting to use it in an indoor positioning situation. So among all these techniques, we propose in this paper to evaluate a new method, okay, a new kind of pseudolite, which are based on carrier phase measurement, and I'm going to show you, to explain you the principle. This is one transmitter, okay? You have one transmitter located as a pseudolite. Okay, so here you have a signal generator, you have two antennas, and on each antennas we are transmitting one code. One code, which means one signal that is equivalent to a signal that is broadcast by satellite. Okay, so for example, if you know the GPS, you know that the satellites are identified by their code, PRN1, PRN2, PRN3, etc. So imagine here, you will have, for example, PRN1 on this on this antenna, PRN2 on this antenna, PRN3 on this one, PRN4 on this one, etc., etc. Okay, the idea is to have different PRN, okay, but on the same signal generator, in order to have the same synchronization. And why we are doing this? Because if you put a distance between the two antennas, which would be less than one wavelength, you are able to make a calculation at the mobile. You calculate, you make carrier phase measurement on code 1, carrier phase measurement on code 2, and making the difference, okay, you will have a distance that will allow positioning. Okay, so what is the principle? You will recognize it is, in fact, interferometry logic. You have one antenna, two antennas. The signal is broadcasted. You have, of course, D1. You have D2. Your mobile receiver is measuring carrier phase. Okay. You make the difference. So you have the difference here. D2 minus D1. It is measured by your receiver, and then this is the equation that corresponds to the distance. So it means that for one transmitter, you are somewhere on the hyperbola. The hyperbola here and here. Okay, this is 2D to make it easier. Okay, but in this case, the associated mathematics on this particular method is the quadrics and the intersection of quadrics. Because of cross-product terms, it's in the general case, it's not an easy mathematical problem. It could be easily solved in very, very particular situation with specific symmetry, but in the general case, it's not so easy. So generally, what is what is preferred, it's something that is used in interferometry. It's simplification, considering that if you are far enough from your transmitting antennas, okay, you are able to calculate. It is the rays are practically parallel, and so you can easily calculate this angle with such calculation. Okay, so for the Greenlock system, so it is the name of the system. The idea is to calculate with two Greenlocks. Okay, you have the intersection of your hyperbolae, and then you have your position. Well, so now I'm going to present you some results, some experimental results that we carried out to evaluate the potential performance of the system. So to do this, we use a spirant signal generator. So the spirant is able to you're able to define a scenario, okay, of which gives you an at the output an equivalent to a set of signals that are equivalent to what you receive outdoors. So as you can change the settings here, what we have done, we have used PRN1 and PRN2. We have make a copy of the ephemeris of the PRN1 on the PRN2. So the only difference of on the pseudo range of the distance that is calculated will correspond to a value that we are inducing in our simulator, in our generator. So we have a situation that is equivalent to 3 Greenlocks. So here you have we have for between PRN1 and PRN2 we put 0 difference. Between PRN3 and PRN4 we put 0.1 cycle difference. Okay, 0.1 wavelength. And at the third element, at the third between PRN5 and PRN6, we put 0.2 cycle. Okay, so then in a guided mode, so at the output of the spirant, we use a mu-blocks receiver, which allows us to get raw data, and more particularly interesting raw data, which are phase measurement, carrier phase measurement, and then we make the difference, and we obtain such result. So, which is interesting here is that, okay, if you see the error, okay, the error is about, here you have in cycle, here in millimeters. So, the error is about a few, less than 1 millimeters of error, okay? So, it means that it was what was expected, because the carrier phase measurement have a particularity that there are less noise than in code measurement, and we want to confirm because this is very specific, the kind of error that can be expected. It's very important because we know that a small error on the measurement can't be transformed to a very big error on positioning. So it's important that in such measurement are good enough to carry out positioning. So this is the error distribution. We show that approximately 80% of the error are less than 1% of the cycle, okay? And so we carried out the same experiment, but this time, instead of guided mode, we use free space propagation. So at the output of the spirant, we put an antenna, and we broadcast the signal in free space propagation, and we get it with another antenna linked to the mu blocks. So the results here are very similar. You can see that here there is a little difference, okay? So, but this difference comes from the fact that the phase measurement are measurement on a cycle, okay? So sometimes it's hard to see, for the receiver, to see the difference between an error of 0.01 and 0.99, okay? So it is why sometimes we observe some very strange measurement. But globally, you see that it is the same, okay? So finally, to rush the goal of our works, we want to use the error distribution that we have collected, okay, in a potentially positioning situation. So we use a mobile receiver for a mobile receiver positioning here, a green lock here, a green lock here, and we apply the error distribution of all the sample, okay, of our collected measurements. So here you have the error distribution, the global error distribution, okay, and finally, what is interesting is here is when you apply this error distribution, okay, we obtain such a figure, okay, and this you see in blue, it is a calculated position. It represents all the obtained position, but of course, globally, the result, maybe here you have only one among the 600 sample, you have only one position. So if you average over 10 measurements, finally we obtain center on the good position, an accuracy of less than 30 centimeters, potentially. Okay? So, finally, what is the idea? The idea is to, of course, using this system to have, adding this system, merge several systems as dynamic positioning using pseudolight, and to merge this system with the other one, because one problem is of the carrier phase measurement is the ambiguity. Okay, so this leads me to my synthesis. Okay, so what have we seen? We have seen that we have no synchronization between transmitters, okay, because the two transmitters are on the same signal generator. We reduce the number of transmitters because two are enough for two-dimensional positioning. Which is interesting is the use of a completely standard receiver, since for the receiver device, the signal that are broadcast are the same as the outdoor signal, and quite good accuracy, potential quite good accuracy, but of course, this requires fully experimental validation in a real environment, and Then we are going to develop the mathematical aspect, which are approximated now. The merging of the approach, it's what I've talked about before, and use of another signal like Galileo or other. So, thank you for your attention.
All right. We have time for one quick question. One quick question over there. And we're going to unplug you because the next presenter is going to be using the machine.
Hello, thank you for the presentation. I'm not sure if you covered that, but what area does your system covers? How many units do you need, let's say, for this room? And you need 3 of them at every room, or how many of them you need per location? Thank you.
Potentially, you mean the range of the system?
Yeah.
It's
yes, pretty much.
It's a good question, but it's not so easy to answer, because one of the problems is that if we use GNSS-like signal, there are problems of reglementation. Okay, so reglementation are very different among different countries. So if I want to give you a very, very quick answer to your question, I would say that the range of such system, if you take the European reglementation, will be okay for such a room, okay? The size of a room like that, okay? But of course, there is another kind of limitation that are not studied in the paper, because the work is in progress, which is the precision, because with such kind of, with the accuracy, because with such kind of system, you know that the farther you are from your transmitters, okay, a measurement error has more effect on the final positioning. So there is a balance to find between that. So I would say, at a quick answer, that it will be okay for a room like that. So thank you.
Okay, so our final nominee is a paper that will be presented by Manuel Lopez, and we're just swapping out computers here. And you can begin when you're ready.
Yep. All right. Well, thanks for giving me the opportunity to speak to all of you and to show you my work. I'm going to be talking about localization using only images in an indoor setting. I think you will find this work interesting even if you're not in computer vision, because I try to mix, in this work I use techniques that are more familiar to Wi-Fi or Bluetooth-based localization, which we've seen here today. So I think it's a good mix of computer vision and other techniques. This will be the outline of the presentation. It's divided in 4 different parts because the pipeline is a bit convoluted, so I want to give a bit of introduction before getting to the actual contribution. So this is the problem statement. There's a database of images which are localized, so we know where these images are in the world. And there is a moving camera, and we want to know where this camera is as it moves around the environment. This basically needs 2 parts. The first part is to be able to integrate evidence over time. Of this, most of you know a lot, and this is what I mean by techniques that you know about. And there's also another important part, which is to be able to describe images and to compare them and to match them to each other. And that's the more computer vision heavy part. I'm going to start overviewing a bit of the first part, how to integrate evidence over time. The most simple way to do it is to use a grid representation. That is, you split the world in a grid. And then as your camera moves around the environment, let's say you have an IMU or you use visual odometry, you know where you are moving, and then you can move your probability mass of where you are within this grid. So your map is always limited to this grid and it cannot escape. So in this example, the camera is going to move north and then west. Your distribution spreads around. And that's how it works. So it's very simple, but it scales very poorly, especially if you add angles, and even more especially if you add full 3D motion. And you have to choose the resolution first. So if you want a 1 meter resolution, then you're stuck with it. Another way of doing it, which is very popular in computer vision, is a graph representation. You build a graph of locations and your movement is restricted to this graph. Again, you're discretizing the world in a sense. And when you move around, your probability mass spreads around the graph like that. It scales really well, even in 6 dimensions. I mean, full 3D motion, which has 6 free parameters. It's a good solution for roads, hallways, and the such. But then again, there's the problem of graph connectivity and how to correct the graph when you reach a location where you were before. And then we can also have a particle filter in free space. Here we're not restricting the motion in any way, and also we are not discretizing the world. So if your particle filter moves around, it spreads. You all know this. So the upsides are that it's continuous. A big downside is, in computer vision, there's a big downside, is that we don't have a smooth fingerprinting map, so to speak, which we have in Wi-Fi or Bluetooth localization. So weighting these particles is not straightforward. And this is where this work has its contribution. Now I'm going to go over some different ways to match and compare images. This is the computer vision heavy part. We can compare 2 images by extracting local descriptors. That is, we look at a small window of the image and we, for example, take its color or its gradients. And we can compare 2 images by counting how many of these descriptors are similar, for example. This has the advantage that we can use projective geometry, which is very well established in computer vision, to reject outliers and the such. But it's very sensitive to changes in appearance. So if you go through a room during the day and during the night, the illumination is going to be very different, and this is probably not going to work. And it also fails when you have a very large data set, when you have many images, because it's a big building or a city. Another way of doing this is using global descriptors. This is, for one image, you have only one description vector, which tries to summarize the whole image. These are much faster to compare, but they also suffer from changes in appearance. I'm going to briefly introduce previous work, which we did before, but it's important for this work, and it's another way of describing images. So the idea of this work was to extract a representation from an image that can be very useful to compare 2 images to know if they are from the same place or not. So in this example, we have 4 pictures of the same location at 4 times the 4 seasons of the year. This is in Norway. And as you can see, the pixels are very, very different, even though it's the same location, right? So we want to extract a representation that is invariant to these changes. We want to be robust to illumination changes, weather condition, people or cars that might be on the street, and also small point of view changes. So we want to get the same numbers out of this image, of these images, even with these changes. And the tool that we use is a convolutional neural net. These are very popular now. And we use a training method that is semi-supervised or weakly supervised. That is, instead of labeling images with their location, what we do is that we take 3 images at every iteration of the training algorithm. The first 2 images are from the same location. Maybe you can see it, maybe not. The first two are actually from the same location, just a bit further back. We have a bus in the first image and a car, which are not there in the second image, but it is the same place. And a third image from a completely different location. And the training method tries to minimize the Euclidean distance of the descriptor vector I and j. That is, the two images from the same place should output descriptors which are close together in Euclidean space. And the images I and k should yield descriptors that are far away in Euclidean space. To achieve this, we use labeled datasets to expose the network to these changes in images which we want to ignore. So we use the Nordland dataset for the seasonal changes, the Alderley dataset for the day and night changes. This is the architecture. It's based on AlexNet, a now classical architecture in convolutional nets. We take only the first 4 layers and we cut it there. And we add a new layer of 128 elements, which is our output vector. The result is that we were able to do place recognition just as well as the state of the art at the time on easy datasets, and much better in datasets which showed these complications. So the takeaway message from this part of the talk is that in this previous work, we developed a technique to extract a compact representation of images consisting of 128 numbers, which is robust to illumination changes and small pose changes. So basically, when we have an image, we take an image from the camera, we pass it through this network, and we get a number, a vector, and this vector changes smoothly with pose changes. This is the most critical part for this work. So if I take an image in this position, and then I shift a little bit and take another one, they will give me similar descriptors, right? Particle filter localization, I don't think I have to explain it too much here. It is the chosen method that we want to use because it is the one that poses this challenge of how do we weigh the particles. This is an animation of a particle filter. There is a weighting step, so you sense the environment and then you see which of the particles are more likely. Then you resample, then you move, and you repeat. So to have a particle filter working, we need a motion model. That is, we need to know how to move the particles. We don't deal with this in this work, but it could be any of the options you have there. Maybe there are more. Ideally, we would use visual odometry, so the camera is the only sensor. And an observation model. So what we are actually proposing in this work is the observation model for the particle filter. So I'm going to repeat, what is the problem when using images if you are not discretizing the world? If you discretize the world in a grid or in a graph, you can take pictures at all of those locations. And then when you get a new image, when you want to localize, you compare it with all of the pictures, and you can rank, and you can see which ones are more likely, which ones are less likely. You can pick the favorite, the nearest neighbor. When you have a particle filter, there's no such thing. The particles are in free space. They are not exactly where you took a picture. So we need some way to smooth out this appearance. And, well, most of you know about this technique because you use it in Wi-Fi localization a lot, and that's Gaussian processes. So the question we want to answer is, how likely is the observation, that is the picture you're taking at the moment, given the map of images that you have and the particle's location? The key concept, as I said before, is that close-by viewpoints produce images that look similar. So if I were to ask the audience, what do you expect to see from viewpoint C? I'm going to say a monkey and a ball. I know they're going to come up. Indeed. And so it's easy for us to predict what the appearance is going to be like. This is another example. Imagine we have a map with pictures A, B, and C, which you can see on the left. And then we have a very small particle filter. It only has 4 particles. and we want to know which one is more likely. And this is the current observation. So given the current observation, the most likely particle is the one that looks similar and has a similar pose also. With pose, I mean position and orientation. So in this case, particle 1 would be the most likely one. Particle 2, even though it's similar in position, it's very different in angle. So it shouldn't be weighted highly. So how do we do this, humans? We try to predict what the appearance would be like at a location, and then we compare it to the observation. But to do this in a computer is not that easy. We cannot predict what an image is going to look like unless we have a 3D model of the environment, and that is of course very costly. And to compare two images to yield a measure of similarity is not that trivial. That is why I introduced our previous work, and that is what we use. So the big advantage of our descriptor is that it changes smoothly with position, so we can interpolate. If we have two image databases here and here, we can kind of predict what the appearance is going to be like in the middle. And also comparing two images is easy with this descriptor because just the Euclidean distance between the descriptors is by design a place similarity measure. So intuitively we know that rotation is more important than translation for image appearance, right? If I take from this position an image in that direction and an image in this direction, we know they're going to look completely different. So we could interpolate taking only into account the angle or taking into account the angle and the position with some weights, but we would have to make a design choice. A better way is to use a Gaussian process that also takes into account the angle. So it's a Gaussian process in 3 dimensions. I'm going to go over this because I think we all know what Gaussian processes are from the previous presentations. So we can automatically find which of these dimensions is more important. Is it more important to turn or to move? Which one makes the images change more? And instead of deciding that, we just do it with a Gaussian process. The kernel is a bit more interesting. This is the only slide with math. Basically, we have a kernel which is a kernel multiplication of 2 Gaussian kernels. The first kernel is the Euclidean distance in position, and the other kernel is the Euclidean distance, the 2 norm of the angle difference. So with a Gaussian process in 3 dimensions, we can interpolate what the descriptor of an image would be like if it were taken from a hypothetical position dx, given a database d1, d2, d3. So this is the whole pipeline in one slide. First, we go to a place, we take pictures, and we have to know where they are. We can use classical computer vision methods for that. And then we find the best kernel parameters by training the Gaussian process on this data. And then in the online phase, when you actually want to localize, you take a picture and you extract a robust descriptor from this picture on your phone. And then for each of the particles in the particle filter, you predict what the appearance should be like at that location, and then you compare the appearance of the current observation with all of those predicted appearances, and you weigh them, and then you move the particles. I'm going to show it's a very short video, so I think I'll play it twice. It's on the so-called Navis dataset. I think there's somebody from this company here. In this setting, we have it's an office-like setting, and we start by spreading out the particles of the particle filter all over. We don't use any map information, by the way, so the particles are going to go through walls and all of that crazy stuff, because we are only testing the computer vision part. That's the environment. We use about half of the images for the database and the other half for a test sequence. And you can see how in 5 to 10 frames, the particle cloud is more or less localized. So very quickly, with less than a dozen images, the particle filter is globally localized. Work in progress, or future work, we also want to do it, we are doing it outdoors. We can use Google Street View imagery, which is already geolocated. So there's a big potential there. And well, our idea for the future is that with the same framework, you can do indoors and outdoors. You should be playing there. It's a bit chaotic, but so the little X marks are where we have images. And after a while, it localizes itself. It's not a very big environment, but oh, that's my talk.
We do have time for a few questions.
Hi, Manuel. I would like you to elaborate a little bit on the dimension of the descriptor.
Okay.
You say 128. Have you made a study on why 128 and not more or less? Because I think it's an interesting question because I guess the dimensionality of that output comes given from the AlexNet network, or you train it with another dimensional?
So the dimensionality, which is actually not this slide, but this slide, that last layer is that we chop off the AlexNet net after those 4 layers. Those are standard, and they are trained on a very big database. So these are already generic computer vision feature extractors, let's say. And then we add this layer of 128 completely new neurons. So all of the connections are randomly initialized, and we train them. As you might know, training a convolutional net takes a lot of time, and we did test with different sizes of that layer, and of course many other architectures. But I wouldn't say that we made an in-depth study of what the optimal size is. I can assume that if you want to describe more places or have more detail, you would like to have a wider layer at the output. Of course, there's a trade-off, because you want a small vector too. You can think of this application as an online application where you have a database and a server, and you want to transfer these descriptors back and forth. So short is also good. So yeah, no real in-depth study of what is best.
Okay, I think we have time for one more question. And I'm blinded up here. I can't see. I think there was one question down here.
Thank you for the kind presentation, for convenience of the people who has not have the prior knowledge of the vision. And my question is that, so in your video clip, the database, there are a lot of database. I mean, we have to take a picture for the training data in the store, in next door. There are too many. So in terms of that, the efficiency, so let's assume there are finite number of training data. Mm-hmm. So what, in your opinion, what is the most probable good landmark for the indoor environment?
You mean in terms of density, landmark density, or?
Yeah, it's like, yeah. So you know, the indoor environment, you know, always see people moving, people closing around.
So let me ask that question. Let me answer. It does sound very troublesome to walk around and take pictures of everywhere and to note down where they are. Just as it is troublesome to fingerprint a location for Wi-Fi. But I think, classical computer vision has a very good solution for this. We can walk around with a camera through a building without stopping. And we can just walk around and take pictures, and as a post-processing step, we can actually calculate where that camera was at every instant. This is called structure from motion. And for example, there have been works where people collect a big database of images from Rome, for example, from a city, and the whole 3D model can be reconstructed from the images. What I mean to say is that you don't have to write down where you took every image, as long as you know where you started. We can just walk around, make a video, in fact, at 30 frames per second, and we will know exactly where each frame was with centimeter precision. And in fact, I think this could be very useful to actually obtain Wi-Fi fingerprinting.
Thank you once again.
Thank you.
Stay here for a second. Okay. Go ahead. So if I could get the other two presenters back up on stage, we have to announce the winner. So, are you still here? I hope you're still here. Come on up. Where's Alexandre? What? Hey. Okay, I don't know what happened to... Alexandre, are you in the audience right now? He's not in... Okay. Well then, I guess we'll announce it without him. I guess we have to move on. So as I said earlier, it was a very difficult decision to pick a best paper. So we have one winner and two tied for runner-up. And we'll announce the winner, right?
Well, there is a plaque for each of you.
Absolutely, yes. So
This is for you, your work. This one is for you.
and we'll accept that on behalf of
Okay.
Alexandre.
The winner is image-based localization using Gaussian processes. Manuel López Antequera, Nikolai Petkov, and Javier González Jiménez. We don't have a second and a third. We have 2 seconds. And they're going to share the second position. So, mapless indoor localization by trajectory learning from a crowd. I'm going to wait to pronounce your names because I'm going to do it wrongly. Thank you. Thank you. We have as well the certified and the plaque for the other selected paper. So we'll try to find him later. So now we're going to, I want as well to announce that, I don't know if you remember that during the poster session you were voting for the best poster, and according to the TPC and your votes, we have a winner as well. So we would like to recognize as well the work carried out by Marco Zindis, Matthias Pelka, and Horst Helbruck, investigation of anomaly-based passive localization with received signal strength for IEEE 802.15.4. I don't know if he's here or not. No? So we'll try to look for him later. Okay, so we can use his email for sending. Okay, so congratulations, and we're going to take a picture.